Okay, let me introduce you the linear versus nonlinear using a predator-prey model. So the model is really simple. For linear growth, we just have dn dt equals gamma n, and we just get an exponential growth. Imagine a bacteria in the test dishes. It just grow without any constraint with sufficient amount of food. Basic unlimited resources scenario, we have a linear growth. So, but once we have we have other species that counterbalance it. For instance, we get into a nonlinear interaction. Basic interaction create the nonlinear system always have a multiple modes interact with each other. For this case, we study a predator-prey model. It just a fox and rabbit. Fox grows, but the rabbit grows, but fox eats the rabbit. But if the rabbit, see this the orange line, rabbit grow and then fox start to grow since it started to see, oh, we have more food, then let me eat it all, and then the rabbit started to decrease. So does the fox, and it cycles over time. That's basically a random scenario with a kind of extreme rapid changes. Um, so so basically the equation can be stated that like that ddt equals alpha x minus beta xy. So the alpha x is a growth, it's a linear term. So we call it a linear term is just basically the growth based on like the rabbit eat grass. And the negative beta xy is just an interaction term. So in the interaction between the result of interaction between rabbit and fox that impact the rabbit basically being eaten. So it's a negative. And similarly, the fox dy dt equals delta xy. The impact of fox due to the interaction of rabbit and fox. Basically, they get sustenance so that they grow. And negative gamma y, basically, if nothing happens to the interaction, they will die out because they don't have things to eat. So it's negative. And for steady state, when ddt equals 0, then we have a relatively simple second order equations. Then we solve for two solutions with such. One is trivial, of course. There's no animals on the land, and it's always steady, and thus another steady state. So this we have another simulation with a initial condition with around the steady state. We have this solution. So map back into a fluid dynamic scenario or plasma mechanics, plasma physics scenario. We can imagine like two mode competing for a driving term, and they're ultimately saturated. Then they will saturate at a certain level, just like that. They're competing for the limited resources, and just like rabbit and fox, they're they're restraining each other, and the interaction, of course, cannot be generalized with can be generalized with somewhat a predator-prey model, but it won't be like just that trivial. But still, it's a really good way to think about it intuitively. You can think, say, one mode, say, say there's a simple linear mode start to grow, and two linear modes start to grow really closely to each other, and then the either spectrally or spatially getting close to each other, and then start to interact. Basically, grow out of the linear phase and go to nonlinear phase, because linear, as we always calculate, is pretty much a local approximation, either spectrally or spatially. Then once they grow out of that phase, it will start to interact with each other. Then it's grow from the linear go from linear, is no linear approximation no longer a good solution. Then we got a nonlinear interaction, just like a fox and rabbit. See, one mode grow higher, and the other mode is, then it grow high to enough height, then it cannot grow any higher because the energy feeding into it is limited. It cannot keep growing, and then the other mode may catch up and to a certain level of saturation, or even alternating, because it could mm, it could maybe in some dynamic way just take the energy of the mode that grow faster, like over time. I mean that happens in the simulation that I have the experience of, but I'm not an expert, so I will just shut up from now. My point is, the nonlinear interaction can be understood as a parody of the predator prey model. So we grow from the linear phase. Is we have an equation that is a really good linear approximation, and then we grow out of that, and then we face the nonlinear interaction. And the predator prey model is very good familiar, so that we can use that as a uh, intuitive understanding of a nonlinear interaction in the complex systems.